So the purpose of this video is to give you an overview of the strategies in solving trig equations. So the first strategy where I'm going to focus on this video is, if possible, rearrange your equation so that there's only one trig function, then isolate that trig function and solve it using inverse trig. And the next strategy, which I'll go through in the next video, is if there are multiple trig expressions, factoring is often a good way to get through the problem. And then the third thing that I'll cover in sort of the one of the later videos is occasionally you have to use something called trig identities to sort of manipulate the equation and to prepare it, sort of put it into one of these two categories so that you can either solve using inverse trig or use factoring and then inverse trig. And then I have a note in red that's really important. In my opinion, the most important thing about solving these equations is that you really need to make sure that you found all the solutions on the given interval and that you didn't include any that you shouldn't have. You really only want to find solutions that are on the interval, and that can be a little bit trickier than it sounds. So just make sure you pay close attention to that. So my first example is this: solve 3 plus 2 sine x equals 2, for that interval between 0 and 2 pi. There's only one trig expression here, so I'm just going to I'm effectively going to isolate the sine x and then use inverse sine to solve the problem. So if I move the 3 over, I'll have 2 sine x equals -1. Divide by 2, we'll get sine x is -1/2. And then here we'll use inverse sine. We'll say x is the inverse sine of -1/2. And this may look like it's a case where I need to use the principal value because it says the inverse sine of -1/2, but note that the problem didn't initially say inverse sine of -1/2. That's something that I did in the problem. When that happens, I need to come up with all of the values that are on the interval that I'm looking at. Right? So now I start working through this, right? So where is the sine -1/2? Well, in the unit circle, that's going to happen here and here. And so you sort of think about what those values are. I mean, the principal value over here is -pi/6. This one over here is 7pi/6. So those are sort of our two categories of solutions, right? It's either going to be -pi/6 or it's going to be 7pi/6. And you'll note that this one is on the interval, but the other is not. Now that doesn't mean that I'm done, right? I still need to find all solutions on this interval, right? Which means adding 2 pi to this one to get x equals 11pi/6 will also give me another solution. So this equation, it turns out, has two solutions. They are 7pi/6 and 11pi/6. This next equation that I have has two trig expressions, sine of 2x and cosine of 2x. And so you might think we need to use some sort of factoring, but there are no powers involved here. Sometimes you'll need to manipulate the equation a little bit to put it into a position where you can solve it. So, I mean, I'd recommend you pause the video for a second, see if you can think of some way to make this thing only have one trig expression in it. If you need a hint, I'm thinking about using division. So if I were to divide both sides by cosine 2x, I would end up with the sine of 2x over the cosine of 2x is equal to 1. And that basically means that the tangent of 2x is equal to 1. And just like that, I've now changed this equation from having two trig, functions into having only one trig function. Now that I have that, I can use inverse trig. So when I apply inverse tangent to both sides, I'll end up with 2x equals the inverse tangent of 1. So now we have to sort of stop and think like, okay, so where is the inverse tangent, or where is tangent 1, right? What is the inverse tangent of 1? So let's see, inverse tangent of 1, that's where sine x over cosine x is 1. So on your unit circle, that looks like it's going to be here at pi/4, and then down here at 5pi/4. Now what's really important here is that those two values, pi/4 and 5pi/4, are now set equal to 2x. So I have 2x equals pi/4, and I also have 2x equals 5pi/4. Okay. So now when I divide both of these by 2, I'm going to end up getting that x is pi/8, and x is 5pi/8. Now, the thing that's kind of interesting about this is that there might be other values on the interval from 0 to 2 pi. Like initially it felt like, oh, we found all the things on 0 to 2 pi, but then we divided them by 2. Like in some sense, these two answers, pi over 8 is like here. 5 pi over 8 is only like here, right? It's just barely more than pi over 2. So sometimes we even need to do things like saying, well, could I go all the way around the circle? Could I go all the way around to, let's see here, what would that be? That would be 9 pi over 4. And say, oh, 2x could also have been 9 pi over 4. When I do that one, I get x equals 9 pi over 8. Right? Similarly, 5 pi over 4, if we add 2 pi to that, so if we add 8 pi over 4, we get 13 pi over 4. We could also have 2x equals 13 pi over 4, which when we divide by 2 would lead to x equals 13 pi over 8. That's still less than 16 pi over 8, which is 2 pi. And so it turns out in this case, we actually had 4 solutions to this one. We had, the pi over 4 type solutions, which gave us pi over 8 and 9 pi over 8. And then we had the 5 pi over 4 type solutions, which led to these two. So we actually had 4 solutions for this one. And then we've got this last problem, find all values of x on the interval that satisfied this equation, 3 secant squared of x over 4 minus 4 equals 0. So this is an instance where there is only one trig expression. Right? I mean, there's only secant, but it's secant squared. So we're probably going to, we'll basically isolate that and then we'll square root to solve for it. So if I move things around, I'll end up with secant squared of x over 4 equals 4 over 3. I just moved the 4 and divided by the 3. Then remember that secant squared means secant times secant, so it really is reasonable for us to square root this and to end up with the secant of x over 4 is equal to plus or minus 2 over root 3. Now we could do inverse secant here, but I don't know about you guys, but I feel like I'm better at my sines and cosines than my secants and cosecants, so I'm inclined to sort of reciprocal both sides here. The reciprocal, but note, I'm not going to reciprocal the inside of this. I'm really, and just to show my work here, I'm really saying that this means 1 over the cosine of x over 4 equals plus or minus 2 over root 3. It's probably easier to reciprocal these and get the cosine of x over 4 is equal to plus or minus square root of 3 over 2. Okay? So at this point, we sort of, we need to split this equation into different pieces. So I can now say x over 4 equals the inverse cosine of positive root 3 over 2. And then x over 4 is also equal to the inverse cosine of negative square root of 3 over 2. Keep in mind, by the way, the interval I was working with was 0 less than or equal to x less than or equal to pi. So when I keep solving this thing, x over 4, so let's see here, where is inverse cosine, what is the inverse cosine of the square root of 3 over 2? That's basically going to be pi over 3 or 2 pi over 3. Right? Similarly on this other side, the inverse cosine of negative square root of 3 over 2, let's see here, so those are going to happen, here and here. We could use negative angles for those, but because it looks like they want us to find positive angles here, we'll come up with the other ones. You may be thinking, by the way, that these two angles are very clearly not on this interval, but we should look at them anyway. We should be careful because when we multiply the 4, things might happen. You can probably already see what's going to happen, but in case you can't, let's keep walking through it. So the two values we come up with here are basically 4 pi over 3 or 5 pi over 3. Then the last step we have to take is we really need to isolate x, right? So when I multiply the 4 over, I end up with x being 4 pi over 3 or 8 pi over 3. And then over here, x being 16 pi over 3 or 20 pi over 3. And then remember that important note, we now need to look at our interval and see what fits. And the sad reality for this equation is that nothing fits. All of these are outside of that range, and that means that this equation has no solutions, right? So we would say something like, this equation has no solutions on the interval. And to be honest, I'd like us to get into the habit of using that notation and using that terminology and writing things in sentences. A big part of the AP exam, at least, and the IB exam to a lesser extent, is really being able to justify your work. And so getting to the end of this and just making a weak statement like no solution is just sort of like, it's true. They asked you to solve, and you can respond, sort of quickly and impolitely by saying no solution. Or we can really say, hey, this has no solutions, ... on the interval. There are plenty of solutions. It just doesn't have any on this interval. So those are a few examples of how you solve for a problem that just has one trig expression. We'll move on to factoring next.